So chapter 4 is about continuous distributions. So we did discrete distributions, now we'll do continuous. And there's two special continuous distributions that are common enough that we're going to learn about them by name. So first you have the uniform distribution. And the uniform distribution between A and B has a flat probability density function. So remember, all of our continuous functions all have some kind of curve that is our density curve. Okay. So it just turns out that this one is always flat, or it comes up often enough that we've named it. So anytime you have a flat density curve, you call it a uniform. And different books have different notations, but ours will use this notation. So it says X is distributed uniformly from A to B. So X is distributed uniformly. Remember, that's what that little curved thing is. That means distributed from A to B. So some things you might notice about this is, if you think about it, probability is always the area under the curve, right? And the total area, or total probability, always has to be 1. So if we were to try and figure out what a formula for this curve would be, or even try and find the area, a rectangle is always height times width, right? Oh, rectangle area. Actually meant to write area there. So rectangle area is always height times width. So in our case, our area is 1. We don't really know what the height is yet. Let's leave a blank space. And our width would be what? We're going from A to B. How would you find the width? Just B minus A, right? If this was from 2 to 5, you do 5 minus 2 and you get 3. The width would be 3. Okay, so if it has to go multiply to 1, my width is B minus A, could you tell me what the height has to be? The height would have to be 1 over B minus A. And so the height equals 1 over B minus A. Now, why would we care about the height specifically? The height is the actual curve, which is our actual PDF, or f of x. So we're going to do some general stuff for the uniform distribution. Let's let x be distributed uniformly from A to B. Let's start by finding the PDF. So little f of x, or just the formula for the curve, has to be 1 over B minus A, because it's just the height of the curve. And that's going to be 4 x between A and B. Now, once you have the PDF, this is actually a really good review of Chapter 2. From their PDF, let's try and figure out our CDF, our expected value, our variance, etc. So, find the CDF. How do you find CDFs if you know the PDF? If you're going from the PDF to CDF, we always integrate, because we're adding up all of those areas. So the CDF, or capital F of x, you always integrate. It says from negative infinity to x, and you're supposed to do the PDF with some dummy variable. But negative infinity, we don't usually start at negative infinity. Usually we have bounds. In our case, our lowest bound is a. So we'll integrate from a to x. And we're supposed to put in a dummy variable t, but there's not actually any x's in our PDF. That b minus a, those are just numbers, just constants. So it's just 1 over b minus a dt. And when we integrate, we get x minus a over b minus a for x between a and b. So again, when you go on and you take other statistics classes and things, they'll give you a distribution and say, this is the distribution we want you to use, and then they'll give you all these formulas. This is how they come up with the formulas. This is everything you learned in Chapter 2. Now, if you want the expected value, for a continuous distribution, how do we find the expected value? We just integrate. If we want the expected value of x, we integrate x times little f of x dx. Remember, whatever you want to find the expected value of, that's what you plug into your integral. And you integrate over your entire bound, so in our case from a to b, x times my PDF, which is 1 over b minus a dx. And that is a plus b over 2. So there's your expected value. Which actually makes a lot of sense. It's the lower bound plus the upper bound divided by 2, so it's basically just finding the average of those two numbers. Which kind of makes sense because everything in between is equally likely. And find the variance. How do you find variance? There's multiple ways you can find variance. The easiest way to compute is usually to find the expected value of x squared minus and then do the expected value of x all squared. So let's first find that expected value of x squared. To find the expected value of x squared, you integrate x squared. So now we put the x squared into our integral, but we still times it by f of x dx. So we'll still integrate from a to b, but we do an x squared times 1 over b minus a dx. And we get this big complicated looking thing, which is a squared plus ab plus b squared over 3. So now let's come down and find our variance. So expected value of x squared means we'll take all that we just found, a squared plus ab plus b squared over 3, minus, and then we do our expected value of x, which is a plus b over 2, but then you have to square that. So the expected value of x, all squared. You have to do a lot of algebra, simplifying, but eventually you get to the point where this is just a minus b squared over 12. So we found our equation for our variance. So now that we found all of these equations, you can use this on every uniform distribution problem from here on out. You don't actually have to do all of this work each time. And then to start our next example, we have a company that makes a hot chocolate mix, and they have a machine that packages their mixes. It's supposed to be a 16-ounce container, but they're not always exactly 16 ounces. And this one happens to vary between 15.95 and 17 ounces of hot chocolate. And it's uniformly distributed, which means that each weight in between that 15.95 and 17 has an equal chance of being chosen. You'll notice that it's supposed to be 16 ounces right here, so they don't go very far beneath it. Why would that be? Because people will complain if you don't give them as much as they want. They don't really complain if you give them more, but you need to make sure you have that at least 16 ounces. So when you look at little f of x, or our PDF, it's just a flat line that goes from the 15 to the 17, or 15.95. Your capital F of x, though, your CDF, it's adding up all of the cumulative probabilities or areas. So you start off with a little bit and then it gets bigger and bigger. But it's still kind of that straight line going up. So to continue that example, let's actually work with it. So a company makes hot chocolate mix, has a machine. Oh wait, we already read that all. Okay, find the PDF. Okay, we don't have to do any work here. We can just, well, not a lot of work. We can remember our formula. Capital F of x, or little f of x, our PDF, is 1 over b minus a. So really, all I need to know is what are b and a. So let's make ourselves a note here that this is a uniform distribution. So x is distributed uniform from 15.95 to 17. So 15.95 is A and 17 is our B. So just your upper and lower points. So we'll do 1 over B is 17 minus A, which is 15.95. So we get 0.9523. So that is our PDF. And you should always tell me what your bounds are on a PDF. So it's for x between 15.59 and 17. Now find our CDF. Normally, to find your CDF, you have to integrate your PDF. But we found a formula that works every time. It's just x minus a over b minus a. So in our case, we'll do x minus a, which is 15.95, over b minus a, so the 17 minus 15.95. And we can simplify this to x minus 15.95 over 1.05. So that's our CDF. Again, you always put on your bounds. So if I wanted to find now my mean amount per package, mean means find the average or expected value. So mean is that little symbol mu. It just means the same thing as find expected value, E of x. And we have a nice formula for that. It's a plus b over 2. So 15.95 plus 17 over 2, which gives me 16.475. Okay, so let's go ahead and start going over this. It might not be quite done yet, but that's okay. So first, when it asks us to find the standard deviation, we don't have a formula for that, but we do have a formula for variance. And variance of x is supposed to be a minus b squared over 12. So we just plug in our a and b and we get 0.0918. So then if you want the standard deviation, which we do this little nice sigma, that's just the square root of your variance. So 0.3029. So again, you'll find that over and over anytime you ask for standard deviation. Find the variance first. And 5, find the probability that our machine underfills the 16-ounce container. So that's saying find the probability that x is less than 16. Well, let's use our CDF to find probabilities. Usually if we have the CDF, we'll always use it because then we don't have to actually integrate, which always saves time. So probability that x is less than 16, that's just saying plug it into the CDF. That's the definition of our CDF. So just plug 16 into your CDF, or capital F. Let's see, so here's our CDF, the x minus 15.95. So we'll do 16 minus 15.95 over 1.05. Which is 0.0476. So again, when finding probabilities, usually we'll just use a CDF because then we don't have to integrate again. But you just plug 16 in. If you did want to use the PDF, the probability that x is less than 16, you would just integrate, okay, and you would integrate up to 16. Where would you start? What would be the bottom though? It didn't give us a bottom, but we can't go any lower than 15.95, so you put that as your bottom. And you just integrate little f of x, dx, etc. until you get to the same answer.